So hey everyone, we're here for example 2 with some scary spiders and some very fabulous jack-o'-lanterns. Happy Halloween. All right, so turning over to the annotator. Here we go. Okay, so here's the second example from Wednesday's lecture. And it deals with a multiple pipe system. And it's kind of a difficult problem. It's a little bit involved because it's not straightforward to figure out which direction the water is flowing in. Is it flowing from reservoir A down into both reservoirs B and C, or is there flow from A to C and also B to C, right? So what we have to do in this case is assume one configuration for the flow, see if the answer makes sense. If not, solve it the other way. So here we are solving it in the other video. Okay, so it's not obvious which direction the flow is in. So first we're going to assume the flow is out of reservoir B. And then see, again, if it makes sense. All right, so according to conservation of mass, the continuity equation, we have now, if you remember from that last slide from the lecture on Wednesday, for multiple pipe systems, we have that Q1 plus Q2 equals Q3, right? We've got our pipe 1, our pipe 2, and our pipe 3. But since the diameters are the same in all the pipes, this translates to a condition on the velocities, that V1 plus V2 equals V3. And we'll call this equation 1. All right, now if we write down the energy equation from A to C, point A to point C, as in the figure, we get the following. PA over gamma plus VA squared over 2G plus ZA equals PC over gamma plus VC squared over 2G plus ZC plus now our major losses due to friction. So F1, the friction factor in that pipe labeled number 1, times L1, the length of the pipe, divided by D1, the diameter of the pipe, V1 squared over 2G, plus F3, the friction factor for pipe 3, times L3 over D3, V3 squared over 2G. But, however, here, we know that PA is equal to PC is equal to VA is equal to VC is equal to ZC is equal to 0, right? So this simplifies to the following, that ZA equals F1 times L1 over D1, V1 squared over 2G, plus F3 times L3 over D3, V3 squared over 2G. Or plugging in numbers, we get 100 feet equals 0.02, the given friction factor for pipe 1, over 2 times 32.2 feet per second squared over 1 foot times 1,000 feet times V1 squared plus 400 feet times V3 squared. All right, then similarly, and this simplifies to 322 equals V1 squared plus 0.4 V3 squared. And we'll call this equation 2, right? So we've written the energy equation down from points A to C and simplified it as much as we can by, crossing out whatever is identically 0 and then plugging in the other values we have. All right, so similarly, we write down the energy equation for a fluid flowing from B to C. And we get ZB equals F2 L2, whoops, over D2 times V2 squared over 2G plus F3 times L3 over D3, V3 squared over 2G. And if we plug everything in, that simplifies to 64.4 equals 0.5 V2 squared plus 0.4 times V3 squared. And we'll call that equation 3. All right, so now we've got equations 1, which is the continuity equation from the previous page, just going back to that, which says V1 plus V2 equals V3. Let's just copy that up here. Okay, so we've got equation 1, then equation 2, and equation 3. And it turns out that there is no solution to these equations that has real positive numbers for the velocity, right? So we've got 3 equations and 3 unknowns, V1, V2, and V3. No way to solve these equations when you try that gives you real positive values for V1, V2, V3. So we know we made the wrong assumption. The flow is not out of B, it's into B. So we have flow from A and it goes into both reservoirs B and C. I'll say therefore flow is into B. All right, so now energy equation we wrote down from A to C is fine, but now we need to write down the energy equation flowing from A to B. So we do that. And the equations we end up with are 1, which is just the same equation. V1 is equal to, or pardon me, actually, 1 gets modified, right? So we're going to call it 1 prime. And we end up with Q1 equals Q2 plus Q3, which leads to V1 equals V2 plus V3. The second equation remains the same. 322 equals V1 squared plus 0.4 V3 squared. But the third energy equation is different. We get ZA equals ZB plus F1 L1 over D1 V1 squared over 2G plus F2 L2 D2 V2 squared over 2G, which leads to the equation, write it down here on the bottom, which leads to the equation 258 equals V1 squared plus 0.5 V2 squared. Okay, so now we have a new set of 3 equations and 3 unknowns, and we get real positive solutions to the velocities here. And when we solve them, we get Q1 is equal to A1 V1. All right, let me put it in terms of the velocity here first. So V1 is equal to 15.9 feet per second. V2 is equal to 2.88 feet per second. And V3 is equal to 13.02 feet per second. And then in terms of the flow rates, that gives us Q1 is equal to A1 V1 is equal to 12.5 cubic feet per second. Q2 is equal to A2 V2 is equal to 2.26 cubic feet per second. And finally, Q3 is Q1 minus Q2 is equal to 10.2 cubic feet per second. And ta-da, there we go. So that's how we solve that problem. So this is a good example of both how to solve these pipe flow problems, whether it's single or multi-pipe for the flow rate rather than pressure, and how to deal with multi-pipe systems and when it's not clear which direction the flow is in. So hope that was helpful. Hope everybody has a great Halloween, and I will see you guys on Monday.